Okay, so in the previous recording, we spoke about matrix vector multiplication, matrix multiplication, and we learned how to manipulate matrices by way of multiplication. Now, this is important for several reasons, but one of them is to deal with this equation here, ax equals b. So a standard linear algebra course, like even an advanced linear algebra course, half the time is devoted to considering that equation. And we're going to start today's lecture by looking at a very simple form of that equation. So here is the form. So we want to solve this system of equations. So surely all of you have seen a system of equations before at some point. Your goal is to find the best x and y that satisfy this equation, right? How did we do that? Well, maybe you learned like how to solve for one variable, substitute back in. Maybe you learned elimination, which is going to be very much related to what we talked about today. But how do you picture this is what I want to really start with. Because I would assume, what does it mean to be a solution for this? Like if you were to like have a picture, what would you think? You can like say it out loud. Like if that has a solution, then you're going to see what in the plane? Any guesses?
It would be a 2x1 vector. Is that what you're asking?
Oh, well, that is a solution, but like there's a picture that's typically associated. But maybe I'll just draw it. So be very careful how I draw these things. So let's see. And then so if you were to plot y as a function of x for each of these, this line would be here, I'm pretty sure. So when x is equal, oh no, so when x is equal to 1, okay, and then this line's here. That's 4. So when x is, no, yeah, and then x is equal to 1, y is equal to, oh yeah, yeah. So we have line on the bottom, line on the top, and they intersect right here. And since they intersect right there, that value, so x equals 3, x equals 1 would be a solution. So like 3 minus 2 is 1, 9 plus 2 is 11. So this is the picture that you're probably most familiar with from a college algebra or pre-calc class. However, there is another way to interpret this. They're both equally valid, although, as you know, I'm a column kind of person. So it'll be the column picture I enjoy more. That's actually what's known as the row picture. So how do we relate these back to linear algebra? Well, we have our coefficient matrix times our variable matrix or variable vector equals our output. Okay, so there are two different ways to interpret this, right? There is the row way, which is x times 1 plus y times -2 is equal to 1. That's that line that's right over here. Why did it go through 1? Did I draw my picture wrong? I'm really annoyed at that picture for some reason. Something's off. When y is 0, x is, okay, no. Okay, no, it's good. This line is here, so this is x minus 2y equals to 1. That's good. And this line is 3x plus 2y is equal to 11. But notice, like, that's like saying this row vector times this is equal to that. So row picture, this row vector times that is equal to 1, gives you a line in space. This row vector times that, so 3 times x, 2 times y, equals 11. That gives you this line in space. And they happen to intersect there. That's the row picture. That's why I call it the row picture. But there's another interpretation to this multiplication. You can also think of this as, so over here, this would be the column side. You can also think of this as a linear combination of the columns of the coefficient matrix. So we can think of this as x times the column 1/3 plus y times the column -2, 2 equals 1, so column vector of 1 and 11. So we can think of the rows times that, or this is a linear combination of the columns. So what is this picture saying? This is a linear combination of the columns of column vectors equals another column vector. So that picture, I can just draw it out. So how many just so four, 5, 6, 8, 9, 10, 1, 2, 3, 4, 6, and 2. So what is this saying? Well, where's the column vector 1, 3? So that's like 1 over up there, so it's like right there. So this is the column vector 1, 3. And then we have column vector -2, 2. So I should probably draw it a little bit higher because this is right there. So that's the column vector -2, 2. So a solution exists here is pretty easy to see. It's just like if those two lines cross each other, then they have to have an x and y that satisfies both of those pictures. A solution here, what is it trying to say? Well, it wants to know, so x and y are just going to be scalar numbers. They're just going to scale the vectors x and y. And they're going to want to be added to this vector. So where is that vector? 1, 2, 9, 10, 11. So that vector is 1, 11. So it's like way up there in red. This is the one we want. That's the vector we want. So how do we get there? Like, can we find scalar? So we know how vector addition works, right? You take that vector and you move it there, and that's that plus that, right? But notice, like, if I move it there, and I go this way, it looks like I could get there somehow, right? It looks like I could get there. Well, I'm telling you that that's a solution to this system. So, oh no, sorry, y was equal to 3 here. I mean, x was 3, y is 1. So let's see what happens. So we're gonna, if we multiply that vector by 1, nothing happens to it. But if we multiply this vector by 3, it's gonna stretch. So it's gonna stretch to what? 3 times 1/3, that's just 3, 9, right? That column vector. So 1, 2, 3, and then 1, 2, 3, 4, 6, 7, 8, 9. It's like right there. 1, 2, 3. It's like right there. So this is that vector 3, 9, right? And if we take that full vector, which is this one, so that plus that, we can just like take it, right? And then stick it right there. Add them together like that, or I could have just taken that one and put it right there. Doesn't matter. But that's going to be, it's going to land on that point, right? We see that 3 9s plus -2, 2. So the 3 and the negative, that'd be a 1. The 9 and the 2 would be 11. It would land right on that point. So the rows will generate hyperplanes. So rows generate hyperplanes. A line is a one-dimensional hyperplane. Whereas rows generate hyperplanes, and we want intersections of those hyperplanes for rows. For columns, we're still dealing with vectors. So columns is like a vector viewpoint. Columns, oh no, I'll just say this, column view, and I'll say row view, because there are row vectors that are doing something here. Okay, now, it might seem odd, but this view here, to me, is easier to think of than this view here. Now, this is the one you're probably most familiar with, right? And it's kind of intuitive, like, do the lines hit each other? Can you like see that, right? But when you get to higher dimensions, like 3 dimensions, 4 dimensions, these aren't going to be lines anymore. They're going to be like planes. So if you have 3 variables, imagine like, it's like, do we have hyperplanes intersecting each other somewhere, right? And when hyperplanes intersect, right, that's a lot harder to visualize than having just vectors pointing around in space that you can take combinations of and get to. Okay, so I'll go ahead and introduce the terminology for this viewpoint here. What this problem is asking in terms of columns is that does the So this is like coming back to this question here. This is like asking, does B exist as a linear combination of the columns of A? That's like the key point for the column picture. Another way of saying this is, I'll put it in parentheses because we're not quite there yet, is B in the column space of A. Okay. And so this is again, so these are both questions, right? It turns out in this case that yes, this vector B is in the column space of that vector. Okay. Now, what does this mean? Well, what is the column space? What am I? This is kind of an abstract term I'm using. So I think what we can say is that, well, not quite. I want to focus in on this problem a little bit more, the one that we were just looking at. Like, I erased it, but let's just, what is it? 1, 3, -2, 2, 1, 11. Okay, so now that we know the two interpretations, the row interpretation, the column interpretation, let's go ahead and solve this simple linear system. These are called linear systems. How do we do that? Well, there is this idea of elimination, right? Which is not something that I want to touch on too much right now. I just want to go back to yesterday and kind of refresh our memory on how we can alter matrices with multiplication. Right, so can we multiply this matrix by anything to make that 3 a 0? Like, what type of matrix can we multiply by? Can someone like write it out? Like, tell me what that 2 by 2 matrix is to make that 3 become a 0? And like, it was the game we were playing, right? We were like, what are we gonna do?
Zero, 1.
So we don't need to do anything to the top row. But if we want to get rid of that 3, we can do -3 from the first row and 1 from the second row. And then -3 of this, added with that, what is it going to do? It'll make a 0 right there. But if we multiply on one side, we have to do it on both sides. 1, 11. Okay. All right, so I need y'all to refresh your memories. So what matrix is going right here? Tell me the entries.
0, so 4 by 4.
Say that again.
I was thinking in my head. 1 second.
Mhm.
Now that we've changed it, is it 1, 0, -3, 1?
We haven't changed anything just yet, but what did you just say? Like, one,
Oh,
oh, I was just like, I want to know this times that. What is that going to give me here?
oh, gotcha. Okay.
So like the first row is not going to change, right? It's just going to, well, I want y'all to answer. I need some feedback because this, I know we just were talking about matrix multiplication yesterday, but we did go over like manipulating matrices with multiplication quite a bit. So basically the first row here is going to be 1 of row 1 plus 0 of row 2. So it's just going to be the same thing, 1 minus 2. And then the second row is going to be -3 of this row plus 1 of this row. So -3 times 1 plus that 3 there is 0. And then -3 times that -2 is minus what? Positive 6 plus that 2, 6, 7, 8. Like that. That many of the first row plus that many of the second row. Remember how we would multiply by a negative number and then give there was a reason like we wanted these ones here so we could zero out all the things below it. Okay, so now what's happened on this side? Okay, y'all have to tell me what's going to go over here because that's just matrix vector multiplication. So what is this? What goes on the right-hand side?
-2.
So it's going to, so which entry are you talking about? Because it's going to be a vector, right?
Yeah. So it takes like the first column, the 1 and the -3, and times that by the 1 and adds it together. So -2 in the top.
No. It's
Right.
1 of this column plus 11 of this column.
See, I get which one I'm picking and choosing wrong, confused every time. It's where I'm.
Yeah. But matrix times vectors always think about linear combinations of the columns. When it's easier for me to think full column versus like entry. So 1 of this plus
So
11 of that.
12. So, but the first one would be 12, and then the second one would be 11. No, 9.
So that product is going to be 1 times this plus 11 times this.
Oh, so it's just 1, 8.
Yeah. See? That's all it is. It's 1 of the first column, 11 of the second column. Add them together. Okay.
But wait, you could also do it as 1 of the first row and then add that together, and then 11 of the second row, and then add that together, right? Wait, no.
No. If you're thinking of it that way, it would be, so if you're going from left to right, like if you're thinking about the multiplication of numbers and you're going left to right, then you should think of it as 1 of the first row plus 0 of the second row.
Yeah.
But if you're thinking column-wise, which I think is easier, you take 1 of the first column, 11 of the second column, and add those together. So that's like and if you've noticed, whenever I'm doing row stuff, I typically move to the left side of the thing. And when I'm doing column stuff, I stand on the right side. It's because of what I'm focusing on mentally. When
I think that's
what's that?
Oh, I'm sorry. I think that's where I'm getting confused, is how we're moving from like right to left and left to right.
Right. So it has to do like, okay, I'll explain exactly how I do this, like a little bit more detailed than what I have been doing. Like what's going on, like deep inside my head, like the really tiny bits. So when I'm thinking column and I'm standing on this side, it's because I'm picking the number, the specific number, the smallest unit I'm picking on this side. And then over there is the thing being a vector. I'm taking a number times a vector, column vector, plus a number times a column vector. So I'm over here because the number is the thing I'm multiplying by, the scalar numbers, it's the first thing I start with. 1 of that column, 11 of that column. Add them together. But over here, the first thing I start with, the number, comes from here. So it's 1 of that row plus 0 of that row. -3 of that row plus 1 of that row. But if I'm over here, 1 of this column plus 11 of that column. 1 of this row plus 0 of that row. And that's why I move from side to side, because my eyes, when I'm over here, are focused most directly on the number I'm multiplying the thing by. Over here, there's rows that way to me. I'm focusing on the number that's going to multiply that row, plus that number times that row. That number times that row, that number times that row. Like, see, do you like get what I'm trying to say? Like, I'm picking the number and then applying it to the thing. Picking the number, applying it to the thing. Picking the number, applying it to the thing. Well, we're gonna have to go one more step. Before I get to that though, what happened to our picture? Right, what's going on with our picture now? Because we multiplied both sides of the equation, so nothing should change, but we have a new system here, right? It looks different. So how geometrically does it change? So we have 2 different pictures now. So what's the row? The row picture is that times that plus that times that is equal to 1. So the row picture is x minus 2y is equal to 1. And 0 times x, and put a 1 there, 0 times x plus 8y is equal to 8. So that's the row picture. And the column picture is x times this column plus y times that column is equal to that column. So x times 1, 0 plus y times -2, 8 is equal to 1, 8. Right, so geometric, so what's the picture here? Okay, so luckily that thing did not change. So 1, 2, 3, 1. So that's the line x minus 2y is equal to 1. But now what is the second line? It's just y is equal to 1, right? Or 8y is equal to 8. So that's the same thing as saying y is equal to 1, so that's this line. So we still see that they intersect at the same points, y1, x equals to 3. So now let's do this one. This is going to be hard to draw over here. Okay, and then 1, 2, 3, 4, 5, 7, 8, 9. I think it's about as high as I can go. Okay, where's this vector? It's 1, 0. One, 0. And now where's that vector? That vector's changed from last time, right? So it's at -2. I'll put the 2 a little bit closer right there. -2, 8. 1, 2, 3, 6, 7, 8. Like that. And where is the solution? 1, 8. Oh, I'm gonna do it in red so we still. You see that there? Now, what is interesting about the column picture, hopefully you can see that. Well, there's like two things to note, okay? First off, did I draw my pictures right? Yeah, I did. Notice now that the second coordinate for these two vectors is the same. You see that, right? The second coordinate is the same, right? And here, that's kind of corresponding to how the second coordinate here is the same. In a sense, it's not exactly the same, but you see that there's change happening, but it's not affecting the full solution. The solution's still there, and I still can probably see that, oh, it's super easy to see now. Look at what type of vector x is. I mean, not x. I'll call this like A1, and this would be A2. First column, second column. This column here has no y value. So however I scale this vector, it's just going to go along the x value, right? And this vector here has the same y value as this. So now, if I just take this guy here and I extend it out, I multiply it by 3. This would be 3 times A1 is right here. And I pick that up and I place it right there. That's a plus 3 times A1. This is A2, 3 times A1. You see how it's going to hit it perfectly now. And then that'll be precisely the sum of those vectors. Right? If y is 1, that stays the same. Oh no, not 3. not 3. How far over does it have to go? 1, 2, 3. No, yeah, 3. It is 3. Because this one's only over by 1. Okay, so let's keep this going, right? It's kind of neat to see the pictures play out. At least I think so. And I don't think I've ever actually done it to this detail before, so I'm kind of curious to see what happens. Okay, so now let's do another change to this system over here. Let's make this a 1. How can we make that a 1? Now, you don't have to, you can multiply by a matrix really easy to do this. And I hope, and you don't have to worry about, don't worry about adding rows or anything. Just make that a 1 it's not going to be you won't have to think about it much, I don't think. What was the vector now? 1, 8. Well, I'm just going to leave top row alone. I'm not going to do anything to the first row, and I'm going to multiply the second row by 1/3. 1 of the first row, 0 of the second row, so the first row stays the same. But then I'm altering the second row by multiplying by 1/8. Sorry, 1/8. So what happens now is that 1 times that row plus 0 times that row is just this. 0 times that row plus 1/8 times that row is just this. And then you can do it column-wise over here, maybe. 1 of this column plus 8 of this column is just 1, 1. Or if you did it row-wise, 1 of that row plus 0 of that row is that. 0 of that row plus 1/8 of that row is that. So now that's my new system. That's my new system. Okay. So what does the picture look like now? So the row picture is 1 times x minus 2y is equal to 1, and y is equal to 1. The column picture is x times 1, 0 plus y times -2, 1 is equal to 1, 1. All right, so luckily this one didn't change much. I can still draw it relatively easily. 1, 2, 3, 1. There it goes. There's that line there, and then y is equal to 1. Is still the same. This picture stayed the same. And now this picture So we have 1, 0. And then we have -2, 1. -2, 1. And then we have 1, 1. And then let's see what happens now. Let's do the very last one. Well, we could already solve it with back substitution, which I should mention. Once you have your matrix in triangular form, where you have the diagonal and then everything above it is non-zero and everything below it is 0, you can solve for the very last variable and then substitute back into the previous equation, and you're going to get a new system, right? And it's going to get simpler as you go up further. Or you can make this the identity matrix and then you're done. So what can we multiply this matrix by to make it the identity? We want that to be a 0. That's pretty easy. We want 1 of the first row together with 2 of the second row, and then that'll be a 0. And then we don't want to do anything to the second row. So we have to do it to both sides. So what happened here? All right, quickly, one of y'all, tell me what vector goes right here. I think the quickest is the column way. Come on. This matrix times this column, what goes right there?
It's 3, 1.
Yeah, exactly. 1 of that row plus 1 of that row. Okay, and then we have the xy vector. And then this will become the identity matrix. Because you take 1 of that row together with 2 of this row, add them together, that gets zeroed out. And then you don't change anything about the second row. And now if you drew this picture, it's really easy. What does this picture look like? It's just for the row picture, for this, it's just x times 1 plus 0 times y is equal to 3, and then x times 0 plus y times 1 is equal to 1. So the row picture just looks like this. Here's y, here's x. So that's the row picture. The column picture is just as easy. We have column vector 1, 0. And then the column vector 0, 1. And then 3, 1 is 1, 2, 3, 1. But notice that we've essentially reduced the columns of the matrix to having just coordinates on the x and the y axis. Which means what? What does that mean? If we've reduced, if there's a sequence of multiplications, okay, I want you to really think about this with me. in the column picture with. There's a sequence of multiplications that we applied to the matrix, which didn't change anything, right? So that eventually we reduce that matrix to these two vectors. What does that mean if I write this down? So if I wrote down, I'm going to use the same matrix I started with. 1, 2, 3, 2, x, y equals to a, b. What does that mean about that system of equations? Think about it. A, B, right? Any A, B. And again, the idea is that we weren't messing with, we were changing the values over here along the way, but we could have started anywhere. What does it mean if we can take a sequence of multiplications on A and eventually land on those vectors? What does that mean if I pick any vector AB? What does that mean? What can you predict about, because you can't always solve systems of equations, right? You can't always do it. There's not always a solution for X and Y. But is there a solution to this equation for any A and any B? Y'all are so quiet.
You're saying for all A and all B, there's
Any
a
A or any
solution
B
X and Y?
that you pick. This will always have a solution.
Is it because the matrix and the vector have the right dimensions?
It's more so than that. It's more specific than that. It's because of this. At the very end of manipulating A in that system, look at what column vectors we got. 1, 0, 0, 1. Okay? At some point. So actually, let's go a little bit further here, right? Like, these numbers, you just like pick a multiple of A and a multiple of B going those directions, and then you'll have exactly those two things, those two entries. But more so, let's look at this in a different light. And maybe this will help you understand the very important linear algebra theory that I'm trying to convey right now. What were the matrices that we multiplied by? That one, and then that one. We have to be sure to go in the right order. I want to like figure out what that one. So 1, 2, 0, 1 times 1, 0, 0, 1, 8 times 1, 0, negative 3, 1. Those are all the matrices we multiplied, right? That one times that one times that one, that one times that one. Okay, so this is like the sequence of matrices that we multiplied A by. But I want to know what this matrix is on its own. So we can get some practice doing some multiplication. Okay. So this times that. Let's do that one first. This times that. So this one will stay the same. 1, 0, -3, 1. All right, so that times that. So I know 0 of that row, 1 of that row, that row is staying the same. And then I want 1 of that row plus 2 of that row. So what is that? 1 and then 1/4. Okay. And then let's do this multiplication now. Let's see. 1, I'm going to do it the column way. That might be easier. 1 of that column plus -3 of that column. So 1. So 1 minus 3/4. 1 minus 3/4 is 1/4. And then 1 times 0, and then -3/8. That's one way to do that. Right? 1 of that column plus -3 of that column gives me that. And then 0 of that column plus 1 of that column gives me the next one. Okay. There we go. That's something I wanted. Why do I want that? Well, look at this. Suppose we have the matrix equation that we were looking at, right? What was it? 1 minus 2, 3, 2, x, y equals to 1, 11. Okay. So what we can say now is that let's multiply both sides of that equation by this. Actually, no. We had 111. AB for any AB. Any AB. So 1/4, 1/4, -3/8, -3/8. Did I do that? Why are they the same? Interesting. Times this matrix here. Times x times y, or x over y, equals that matrix times that. I hope I did all my calculations correct and in the correct order. Yeah, that should be fine. Okay. So then I want so what's my new matrix going to be? Maybe 1 of this column plus 3 of this column. So that's 1/4 plus 3/4. So that's just 1/4 plus 3/4. It's just 1. And then -3/8 plus, so -3/8 plus 3 times -3/8 is, what is it? -12/8. Oh, what is that? 2 times, so that'd be 3/2. Wait a minute, something is, I've made a mistake somewhere. Where is it? Where is it? Where is my mistake? Let me find it real fast. In 1, these two matrices made that one. So then this is in 2. These two matrices made that one. And then this will be in 3. 1, 2, 1, 0, 0, 1, 8, 1, 0, -3, 1. All right. So let's make sure that everything is fine. And we know, by the way, that A times B times C is equal to A times B times C. So it doesn't matter the order in which we multiply these things by. I bet you it's this -3/8 here, or something like that. That might be the problem. So 0 of that row, 1/8 of that row. So maybe it's that matrix is the problem. Okay, so maybe let's do that. So 1 of that row plus 2 of that row. So 2/8 or 1/4 for sure right there. All right, 1 of that row plus 2 of that row. Next row, 0 of that row, 1 of that row. We're multiplying now this guy. Just ignoring that for now, starting over. Okay, so 1 of that row plus 1/4 of this row. So then we have 1 plus the 1 of that row plus 1/4 of that, so minus 3/4. Okay. So what was that? So yeah, 4/4 minus 3/4. That is 1/4 in this entry here. And so 1 of that row plus 1/4 of this row. So this will be a 1/4 for sure here as well. And finally, 0 of that row, 1/8 of that row. So -3/8. Oh yeah, see that was my problem. 0 of that row plus 1/8 of this row. This would be a 1/8 right here. Out of 3/8. There. There. Okay, now it's fine. All right, so what does this become? So we have 1 of this column plus -2 of this column is going to be the first column. So 1 of this plus -2 of that. So, no, sorry. 1 of this row plus that. 1 of this column right here, just whenever it gets like that, I'm standing on the wrong side, I'll just write it out. 1 times 1/4 plus 3 times 1/4, 1/8. That's gonna be the first column. Okay, there's a, trying to brush it now. 3/8. So 1/4 plus 3/4, there's a 1 right there. Negative 3/8 plus 3/8, 0. Finally, okay. And then for the second column, it's going to be -2 of 1/4 over 3/8 plus 2 times 1/4, 1/8. Okay. So what's going to happen here? So -2 of that plus 2 of the same thing, there's going to be a 0 right here. And then -2 of this is -6/8 plus 2/8. Is that right? -2 of that row plus 2 of that row. So what does this become? So this will be 2/4. So -2/4. That's 2/4. So +6/8 plus 2/8. Yeah, perfect. +6/8 plus 2/8 is be 1. And then that was that times that, and then we have x, y. And then what is this equal to? This is equal to a over 4 plus b over 4, and then -3 over -3a over 8. Oh, I can do this more compactly because they have the same denominator. A plus b over 4, and then -3a plus b over 8. Okay, so what is this telling us? Like, well, explicitly, it gave us a formula to solve this system for any choice of A and B, right? Like, what were the original choices? 1 and 11. Put a 1 in there. What do you get? So 1 and 11, that's 12 over 4, 3. And then -3 plus 11 is 8 over 8, 1. So you get a 3. You get a 3 and a 1 as a solution, and it works fine. But more generally, what it says is this. It says that, so how can we do this? So if we look at, okay, I'm trying to think of the best way to describe it in terms of the formal definitions that we're about to find. Well, first off, before I even get to that, this thing right here, this is called A inverse. That is the inverse matrix of this matrix A over here. And it's always the case that A inverse times A is equal to the identity, and A times A inverse is equal to the identity. Not all matrices have inverses, but this one does, and it's because it's special, sort of. A lot of matrices will have inverses, but sometimes they don't. What it says is that, oh, this is it. Perfect. The fact that we can invert it and get a solution for x and y means that we can find x and y so that this holds. First column of A, second column of A equals A over B for all A and B that are just real numbers. That's what we just learned. Which means that any, and what does this imply? This implies that any vector in R2, well, let's say it out. So what this is shown, because we can find an inverse, right, and find a solution for x and y to this system for any choice of A and B, that means that because A and B were any real numbers, any vector in R2 can be written as a linear combination of the columns of A. Any vector in R2 can be written as a linear combination of the columns of A. Okay. This is important. What this means is that that the columns means that I'll go ahead and introduce the definition. Column space of A, and that means the set of all possible linear combinations of the columns okay, that's the column space. The set of all possible multiples of or linear combinations of the columns of A. So since we can write any vector in R2 as there's a solution x, y for any A, B, right? We say that the column space of A spans R2. That is, it is what's called, it is a basis for R2. So this notion of basis, spanning, column space, these are all advanced topics in linear algebra. These are what you would see in depth in Math 3423, Advanced Linear Algebra and Optimization. When I took linear algebra at U of H main campus, we encountered this very early on in like an intro of linear algebra course. But things have changed since then, and now basic linear algebra is about procedure. The advanced linear algebra is about understanding how these spaces of vectors behave. So, what does that mean about? So, okay. First off, finding solutions to AX equals B is important for many different reasons. So understanding when a solution exists is important, because sometimes they will not. And if the columns are they are a basis or span the space that they're in, then that means you can always find a solution. But when do they do that, right? When do they do not do that? When can they not do that? This is a fundamental question. And it's like half of all of linear algebra, so understanding that. So let's look at an example when this doesn't happen, right? When can this not happen? Actually, I want to check something real fast. What is the norm of these things? I want to know the norm of the columns. So that column 1, 3. So it's 1 squared plus 9 squared. That's equal to root 10. And the other column, negative 2 squared. So it's just 4 plus 4 equals root 8. So we know where these vectors live in space, these column vectors, right? Like, right there. 1, 3. That's like A1. And then negative 2, 2. That's like A2. 1, 3, 2. So I'm going to do something that I've mentioned before. I'm going to normalize these vectors, these column vectors. And you normalize a vector by dividing by the norm. So like this will be 1 over root 10, 3 over root 10. This will be negative 2 over root 8. It might be beneficial to write this as, to rationalize this, or not rationalize it, but write this as 2 root 2. Just because it might divide out easier or whatever. So I'll say A1 is going to go to the vector. And by normalize, we're going to shrink these vectors down to their unit length, where they each have length 1. So A1 is going to be 1 over root 10 and 3 over root 10. I'm doing this out of curiosity, by the way. So that's the normalized version of A1. And then minus 2 divided by 2 root 2, that is going to be minus 1 over root 2. And then 1 over root 2. So I'll just call this vector here B. It's like the normalized version of A1, and I'll call this one W. And I'm curious to look at B transpose W. I want to know roughly what the angle between them is. These vectors have unit length. They have length 1. So this is going to be 1 over root 10 times minus 1 over root 2. Now they're not orthonormal. That's what I was hoping. And I'll explain what that is in a moment. So then this would be 3 root 10. This is a waste of time. It's not doing, I was hoping for something, but it's not the case. I should have seen it, but they're not, because this is going to be,
Hey, Dr. Davila, I think your recording paused.
oh yeah, I did.